So it'd be great to hear if people have done this before. That's great. Let us know if you've got any questions in by the messenger, in the chat, and so on, or emailing in, as we said. So the topics we're going to cover is binomial probability, cumulative binomial probabilities. Then we're going to move on to the normal distribution. So for the A level now, the two main distributions you will cover are binomial and normal. And they're quite different, but there's a way of linking them, and we need to be absolutely crystal clear on the differences and the properties. We're also going to then go into hypothesis testing, which is very like jargon heavy, lots of rich language in there, and we need to break the questions down. So we'll look at the language of hypothesis tests, and then we'll do hypothesis tests specific to the binomial distribution and specific to the normal distribution as well. So quite an ambitious amount of content to take on, but we're going to hit it now and get straight on with it. So first thing, the binomial distribution. Now this again, every exam board will cover this. Again, since the 2017 reform, this is one of the topics that is absolutely consistent across all of the exam boards. So we're going to start just reminding ourselves what the binomial probabilities are. And it's kind of an extension of ideas we saw at GCSE. So where we did tree diagrams at GCSE with only two outcomes, this is effectively what a binomial expansion, or sorry, binomial probability is an extension of. So if we take a random variable X and it can take a range of particular values in a sample space, and basically what we're looking at is discrete random variables. So actually in this case, normally only whole number values, like amount of cold calls that turn into sales or that sort of situation. So this is what discrete means. This is a key difference from the normal distribution, is that it can only take certain values. And you might think, yeah, I'm fine with that. I know when it's binomial, I know how to spot it, but we're going to look at the notation carefully as well. So the binomial distribution is basically used to estimate the probability of the number of successful outcomes in multiple trials. So the reason that this is an extension on tree diagrams from GCSE is you don't want to draw like a 10-branched set of tree diagrams. You just want to understand the process. So the notation we use is we say that X, the random variable, follows the binomial distribution with N, the number of trials in total, and P as the probability of success of each trial. So this is probability of success of each trial. So N was number of trials. And people do find this notation a bit weird, and they kind of think, how do I even say that? So we say X follows the binomial distribution with N number of trials and P is the probability of success. Now, another question they love to ask is actually the conditions under which the binomial distribution is appropriate. So these are the kind of 4 conditions that we want to know, and we want to be really confident with these. So first of all, the fact that it's called the binomial, referring to 2, there are 2 possible outcomes, success or failure. There has to be a fixed number of trials, so N doesn't change. The trials need to be independent, so every time it's a new go, same situation again. It doesn't remember what happened before. And the constant probability is the final crucial thing. So the chance of being successful each time does not change. It's independent. It doesn't have a memory of what happened before. So these are the conditions under which it's appropriate to use a binomial distribution. So make sure you know them. And we don't want to forget any of those because we're often asked to explain why it's appropriate. Conditions for binomial. Okay, so let's push on and look at the actual formula for doing this. So sometimes people see this formula and they think, oh, this looks really awful. And am I giving it? Can't I just use the calculator? Absolutely. Most of the time you are going to use the calculator for this. but it is quite good to understand where this comes from. So we have this as the binomial coefficient, and you recognize it from pure maths as well. For when we do binomial expansion. And then what we also have is if we actually look at what the binomial distribution is doing, is there's kind of three distinct parts. And this is where I put this in the context of a massive epic tree diagram. If I have 10 branches and I want 7 successes, it's like win, 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 win 7 times and lose, lose, lose 3 times. So you times the probability of success to the power of how many wins, multiplied by the probability of fails to the power of how many fails there are. And of course, because there's so many different combinations, that's why we times it by n choose r or n choose x. That coefficient, that binomial coefficient, tells us how many ways there are of arranging it. So what this gives us is the number of ways of arranging basically X amount of successes in N amount of trials. You know, when you have a long day and you think, have I spelt successes right? I think there's a lot of double letters there. I think that's right. Anyway, you know what I mean. That's good. So N amount of successes, sorry, X amount of successes in N trials. Then what we've got very simply is probability of success of the amount of successes we want. And I'm not going to say of success, I'm going to say of successes again. Hoping I've spelt it successfully. And then this will be the probability of failure. And we're kind of timesing it all in. Okay, right. So, for example, and just make sure we're happy with that choose notation on the calculator. So 3 choose 2 ultimately works out 3 factorial over 2 factorial, 1 factorial, 3 minus 2, which come out as 3. Okay, 6 over 2. Now, let's push on with this and let's look at this question here. So we've got a 4 marker split into 2 marks. Greg and Tim are playing a game of Yahtzee. The game lasts for 13 turns. On each turn, Greg and Tim both throw 5 6-sided dice to try and match numbers they roll. So on his first turn, Greg manages to get a Yahtzee, which means all 5 dice have the same value in a single throw. Explain why the probability of this happening is 1/6 to the power of 4. And the second question says, over the course of the game, Tim manages to get a Yahtzee in a single throw 3 times. Calculate the probability of this happening. Your answer should be given to 3 significant figures. Now, a few things to consider. The key information in the context. We've got to think about why this is 4 and not 5. So that might be quite kind of key to think about. Remember to round in the correct way. And there's lots of key information here. So do start this ahead of time already. I will work this through with you. It's an explain why. So look out for that command word. And we need like 2 marks of reasoning. Probability. This is the thing we're looking at. Understand the context. All 5 dice have the same value. 13 turns. 5 6-sided dice. And then we're going to have a little look. So this is tricky, and this is the kind of question that I would feel a little bit kind of, oh, there's too much to take in information here. How am I going to do this in a couple of minutes? It is quite daunting. The second part is just to calculate, though, 3SF. So we'll start working this through together shortly. I'll just give you a minute to kind of digest that. And well done if you've already made a start. Okay, so we'll start looking for it straight away. For part I, where we're looking to find the chance of all 5 dice having the same value, what we need to interpret is what's happening. So each die is independent. First die can actually have any value. So when you were looking at it and you're thinking, why is it 1/6 to the power of 4 and not to the power of 5? Well, weirdly, it doesn't actually matter what we throw first. It matters that all the others are the same as it. So the next 4 must actually match this value. So the probability of each die matching that first die's value is 1 in 6. So what we've got is 1/6 times 1/6 times 1/6 times 1/6, which is a 6 to the power of 4. Now, this was an explain why question. And for those that attended the session yesterday, we set this out very sort of similar fashion. We want to kind of deductively go through and say, well, this is what I know. This is what it tells me. This is the probability. So this is how I combine it. And then it's quite conclusive. And going through that thought process can actually help you work it out. So yeah, the context we had to realize was the first one doesn't matter. And because it was a show that, we could have almost made that leap and got that ourselves as well. So well done if you followed that. The next bit, let's do a bit of calculation. Oh, sorry, yes. So because it was a 6 times a 6 times a 6, and they've all got to do that, you could have also thought of it as 6 times all of it times together, which would have cancelled to the same thing. I think this was more logically how we discussed it. Okay, but it is effectively the same as the calculation at the bottom there. Right, let's do part 2 of the question. So this one, we want to work out the chance that it happens 3 times. Now, the results of the die are discrete outcomes. There's 2 outcomes, Yahtzee or not a Yahtzee. This is very common, actually, that they'll use the first part of the question to inform the probability for the second part. Now, it is a fixed number of trials, and they are independent, and the chance of a Yahtzee is always the same. So we are actually establishing a binomial distribution here that's pretty involved and just directly comes off the back of what we just did. Okay, so we're creating a binomial within question 2. So what we know, just check that that fits the framework for a binomial, is there are 13 turns for this part of the question. So 13 chances for success. So 13 is therefore n. Now, the chance of throwing a Yahtzee is basically the probability they gave us, they gifted us in part A. So 1/6 to the power of 4, which you could work out if you wanted. You got your calculator, you could give that as a fraction, 1/1296. That's the probability of a successful Yahtzee. Then what we're going to do is we're looking for the probability of exactly 3 in 13 goes. So this means the number of successes is 3. So n is 13, x is 3, and p is 1/1296. Now, for some of you, you can plug directly into that formula. Many of you are very confident with your calculator and recognize that you could use the binomial PD function, not the cumulative. We're not looking for a tail of events. We are looking for a specific event, which is this particular value. Now, this formula will work perfectly, but why not make the most of the calculator that will just do that for you? Because we should get the same outcome. And actually, if you've got 2 ways of doing it, even better. I'm going to anticipate it's a very small number. So we plug those values in, got some tiny numbers in there. And our final answer, the chance of getting 3 of those in 13 goes is 1.3 times 10 to the minus 7. So ridiculously small. Very, very unlikely. Okay. So well done if you also used the PD function for that. That was really good. what we're going to push into now is using the cumulative binomial probabilities, because this will help us later for hypothesis tests. So a cumulative probability density function models the probability that a random variable will take a value less than or equal to X. So sometimes it's like the chance of 3 or less wins, or 5 or more. So it's a tail of events. So here's an example. P of X is less than or equal to 2, which of course would be loads of stuff added up. Okay, so you could work them all out separately using the PD function or the formula, but actually a lot of you are familiar with the CD function on the calculator, which will just find all of them added up. So, or on a statistical table at the back of in the formula book in the exam, that's useful as well. So if you're happy using that, hopefully we are, let's try this question now. Here we go. So a few things to consider. So a carnival game involves drawing a token from a box. There are 20 tokens in total, 1 gold, 2 silver, 4 bronze, which win a respectively win a prize. Jess plays the game 8 times to try to win the prize. That's important as well. It's very easy to mess up what N is for this question. Calculate the probability that she wins at least 2 gold prizes, between 3 and 6 inclusive prizes that aren't gold. Okay, I'm actually going to give you 3 minutes to attempt this. Set it up properly as a binomial, use your calculator, and see how we go. I think this is a really good one to practice. Brilliant. Here we go. Give it a go. So really look out for what N is, how many times she's playing the game. All the other stuff sort of informs us for the probability. So be really careful setting this up. We'll check in a couple of minutes, see how we go. Well done. Okay, so quite a lot of information to take in. Let's give it a try. So let's see how we go. Okay. So to start with, we're going to determine the variables for the binomial. So we need to basically for the first part, work out the probability of more than 2 of the 8 being gold. Okay, so 8 tokens are being taken out of the box. This means that the number of trials n is 8. So there's 20 possible tokens and only 1 is gold. So the probability is 0.05. The only way that this fits binomial is if you put it back in and it's the same probability every time. And that's what we're doing. So the chance of success is a 20th each time that you pull out the gold counter. Okay, so that's P, that's the probability of success. Now, we need at least 2 tokens to be gold. Okay, so what that means is we actually want 2 or more. So that would be great if you got 2 gold tokens, or 3 or 4 or 5 or 6 or 7 or 8. 2 or more will be what we want. Okay, so this is a tail of events. This is actually an upper tail of events. So to correctly calculate this on your calculator, greater than or equal to 2, some of you will have a calculator that can do that. But if your calculator only does binomial cumulative from below, you will have to do this method where you do 1 minus the probability of less than 2. So basically 1 minus less than or equal to 1. But if you've got a calculator that does the binomial upper tail, which I think the CG50 does, that's a real advantage. But because this was an upper tail, if you haven't got that, you'll have to minus 1 minus the lower tail, rather. So just make sure you've done it the right way round. It still should be quite a low probability. So like do sense check that value. Well done if you got it. Right, so just to be clear, because for the normal distribution, we can be a little bit sloppy with the notation. The strictness of the inequality is actually imperative for this kind of question. So this said, the wording of the question, if we look back, implied it had to be greater or equal to 2. At least 2 gold prizes means 2 or more. So that's greater than or equal to 2. If you put a strict inequality, you're doing the same as greater than or equal to 3. So because you wanted to include 2, this is really important for the binomial. The binomial, the inequality matters. For the normal distribution, doesn't matter as much because it's cumulative. Because it's continuous. So this one, yes, this is really important that we get the strictness of that inequality right. And obviously it will change the answer. So for part 2 of the question, we want to determine the variables for the binomial distribution. So we need to determine the probability of between 3 and 6 tokens being bronze or silver. So there's 8 tokens, so n is still 8. 20 possible tokens, 2 are silver, 4 are bronze. So actually there's 6 20ths of a chance that we get a bronze or a silver, which is 0.3. 30% of the time on any given go, that will happen. So that's our binomial. It will be n as 8, p as 0.3. And we want between 3 and 6, inclusive. So again, some of you have a calculator that can cope with that. But if not, what we can do is look at how we could split these tails up. So this is what we're doing. Between 3 and 6. So you could do this as the probability of less than or equal to 6 minus the probability of less than or equal to 2. And that will leave 3, 4, 5, 6, like everything in between. That will give us our answer. That'll be about 45% of the time. So hopefully that's all good. I think that was a really good question, actually, because it wasn't like your normal tails. There was a tail in a kind of thing in the middle, a region of events that we had to look out for. So well done with that. We're going to push on to the normal distribution now. Here we go. So The normal distribution is quite different. First off, because it's continuous, there's some really special properties for it. So it'd be great if you can kind of heavily annotate your diagrams and stuff here. Again, this is one of those things that's been added to all the A levels. All the exam boards have got to test this. So this was set out in 2017. A lot of them tested it before anyway, but now it's been packaged into the A level in a very consistent way. So key things, key features of the normal distribution. So it's a probability distribution model for continuous random variables. It's pretty perfect in the shape that it is. And there's some really key properties to look out for. So it's a kind of bell-shaped curve. So it's this kind of perfect picture here, bell-shaped curve. And it's a continuous random variable that can actually take one of an infinite amount of values. So it's a kind of strange concept. So it's a continuous one, which is very different to the discrete binomial we just saw. Now, the normal distribution is a probability density function that models actually naturally occurring situations, heights, weights, for animals, for plants, for anything, things that have this sort of distribution where the mean, the median, and the mode are all the same. They're all in the middle, and there's a natural kind of variation above and below. Few other properties to just pay attention to. So the way we denote this distribution for a start is we would say X follows the normal, and the population parameters we care about are mu and sigma squared. So already looks very different to the binomial. Key thing to also add is mu, which is our population mean, is actually equal to the median and the mode. That's a fact you would be expected to just know for this distribution. And sigma is talking about the standard deviation. So loosely speaking, that's the average distance of anything from the mean. So just a quick point on notation. Mu represents the population mean. X with a little bar above it represents a sample mean. So don't confuse those. Other key properties of the normal distribution. Oh, typed in for me. There we go. Is it's symmetric, perfectly symmetric. Points of inflection at mu plus or minus 1 standard deviation. So this is our link to pure maths. We mentioned points of inflection before. Points of inflection are where a function changes from concave to convex. So it actually like changes shape. And they perfectly exist 1 standard deviation away from the mean. And the other key thing to consider is the total area under the curve is 1. Now, thankfully, you don't have to do this at A level. I don't even remember doing this at university, but that would mean technically that if you integrated it, the area under it would be 1. Thankfully, we don't have to integrate the normal distribution curve, but that's something we need to consider. Okay, so this value here, let me just annotate that on, is mu minus sigma, and this is mu plus sigma, and this is mu. Okay, few other key points. Now, this is generally for a lot of the exam boards, your textbooks and stuff will write this in. There are some key amounts to know. So generally speaking, 68% of the data, it's worth knowing this kind of by heart, lies within 1 standard deviation of the mean, basically there. Please do send any questions in. As we said, we've got the live messages to the tutors and by email as well, because I understand that this is quite full on at this point. Now, 1 standard deviation of the mean includes above and below. 68% of the values will lie there. Within 2 standard deviations of the mean, that will incorporate 95% of the values. And then three 3 standard deviations above and below the mean is almost like 99.8% or something. So when you're picking a value to choose that covers everything, if you go 5 standard deviations above or below the mean, that will pretty much cover everything for the level of your calculators. So that's worth knowing. You can be expected to know those kind of figures. And so we're going to see that in a kind of question now. So this is a really good one, actually, because it matches the graphs to the shapes. So let's explore this now. So on the next page in your booklet, you're going to see 4 graphs, the X value of their turning points, points of inflection, and also we need to look and reason why, which one isn't a normal distribution, which one is a normal distribution with the lowest variance, and which one has an area between minus 1.6 and 3.6 equal to 0.95. So have a little look at the graphs now. I'll put them up. These graphs. Hopefully you can see them in your booklet. Now, referring back to the question, we need to pick out the 3 that represent that information there. Some of this is quick. You can do this by elimination, process of elimination. I'm going to give you 1 minute to have a little think about that, and then I'll guide us through. But give it a try. Quite a nice question, hopefully. Right, I'm just going to carry on, guys. So let's have a little look at these. I do want to clarify a few things about what values you input in your calculator as the upper bounds and stuff. But I'll do that as we approach the hypothesis testing, because at first we want to just get familiar with how these look. So to start with, if we look at each of these, I'm hoping that one of them really stands out to everyone as clearly not perfectly symmetrical. So the one that's not, that's right. So the one that's not a normal distribution, hopefully we're going to identify is the one at C. So straight away, it's not symmetric. So the kind of, you can also see from the points of inflection, they're not equally far apart. So that one straight away is not a normal distribution. So now we've got the other graphs. For part 2, we want the one with the lowest variance. So this means that the spread, if the variance is low, then it would also have the lowest standard deviation, meaning that things aren't spread that far from the mean. So this is the one with the kind of sharpest peak, the one where everything is more compact and spread closer to the mean. So this will be graph D. Now this bit, interpret this one. If this is 95%, remember this means it's within 2 standard deviations of the mean. So looking at that information, we can actually work out that that would have to have a mean of 1 and a standard deviation of 1.3. So the only one that matches that is this graph here. Now we'd already narrowed it down to A and B. But what we were saying, just to revisit that, because I know that was quite quick, is that it was using that fact we mentioned earlier, that 95% of the stuff lies within 2 standard deviations of the mean. So we know the region we're looking at. And so this and this must represent mu plus or mu minus 2 standard deviations. So we can form simultaneous equations to find out what mu would be and what sigma would be. So this was again a matchup and a process of elimination. And we can see that that would be graph B. So what we'll do, we're going to move on to calculating probabilities. before we get on to hypothesis tests. So what we're looking to do here is, if we're looking to find the value of the probability between two bounds, we are effectively looking to find the area between A and B. And remember, I said the strictness of the inequality doesn't matter so much for normal distribution, because the area of a line is like, it doesn't count. So if you put strict or non-strict inequalities, the answer would be the same. So this is what we're looking at. So what we're going to do is we can say that the probability of X being less than A, I would say in your calculator, loosely speaking, if you have to put an upper and a lower bound, I'd say mu minus 5 standard deviations, but you could use 10, you could just use a massive, like minus 1,000,000, any number you know that's like well out of the way. What that will give us is the area below here. Because after a certain point, the answer in your calculator would stay the same. So that's the value below A. And then the value below of X greater than B would be like the probability of from B up to mu plus 5 standard deviations would be all of that. And so the difference would be the bit trapped in between. Now, of course, your calculators can just work out the in-between bit, a lot of them. So there's a couple of ways around how to do this. But what we're getting at is this is all to do with areas. So we're going to see this, and we're going to see this in a couple of different contexts. The next thing I do want to look at, though, is understanding the standard normal. So the standard normal, this used to be used a lot more because we had to standardize. We didn't have calculators that could do this. So this is an important exam point. If you look at old exam papers, like I'm considering old as pre-2017, the marks will be like quite high for a lot of these easy questions because you didn't have the calculators that could do it. So you had to use this process here. Now, this stuff still comes up. The standard normal Z is basically the normal distribution where the mean is at 0 and the standard deviation is 1. So mu is 0 and sigma is 1. The reason that this is useful is every other normal distribution can get transformed onto it. So we can shift it and shrink it down and then read off the values from a table. So that's why the standard normal basically was used. So everything could be transformed onto one normal distribution. And the process for doing this, standardizing or normalizing, was to shift all the values by the mean and then divide it by the standard deviation. And it perfectly shrunk the graph that we had onto the situation we wanted. So basically Z is going to be X minus mu over standard deviation. So we can rearrange this if we have unknowns in the question to find sigma and find mu. So this is really important. So the whole idea is that we're shifting any normal distribution we want onto this standard normal. Okay, and I'm going to show you what I mean now. So there's a random normal distribution. There's the standard normal. They are graph transformations of each other. So it's like this is like B f of x minus mu over sigma. What we've got is if I move this mu to the left and shrink it down by sigma, it lands up on 0 with a standard deviation of 1. So we're basically describing any normal distribution as a graph transformation to the normal, just to the standard normal. So kind of this is kind of the other way round, but what I'm saying is this is any normal distribution. It could have a mean of 250. And what I'm saying is if I shift it to the left by 250 by the mean amount, the mean is now on 0. And then I shrink it down to 1, then it's got the standard deviation I want. So it's a little bit weird because this looks taller and bigger and stuff. But oh no, here we go again with a pen. One sec, guys. Hit that wrong bit of the screen, didn't I? Um, Apologies for that. I thought I'd learned where not to click. But there we go. So this is what we're saying is anything can be transformed onto this. So we kind of need to see it with a question. But basically, as long as we remember this thing here, this is the graph transformation to take x back to the standard normal. You minus the mean from all the values, you divide it by sigma, and it lands exactly on that perfect Z normal distribution with mean of 0 and sigma as 1. What I'm going to do is I am going to push on, look at this question so that we can then start looking at hypothesis test questions as well. So I know there's a lot going on here. Have a little look at this. I'll guide you guys through it. Take a minute to read through, and then we'll obviously use your calculators as well. We'll start going through this together. Another really good example question. Okay, so for this one, lots going on here. So yeah, just to reiterate, with the normal distribution, that Z equals X minus mu over sigma, that is the transformation to take you from any normal distribution to the standard normal. Right, this question here, Engineering Monthly, is planning a segment called World's Greatest Skyscrapers, and it shortlists 850 potential candidates. Their heights follow a normal distribution with mean as 425. So immediately we can say mu is 425. The judges select a building at random, given that there is a 70% chance of them selecting a building shorter than the 508-meter sized building, which is a key value. Calculate the variance of the heights of the shortlisted buildings to 3SF, and the judges decide to instead include any building shorter than 300 in a separate segment. Calculate the probability of a randomly selected building being in this segment. So there's quite a lot going on, a lot of context, a lot of numbers as well. So let's have a little look. And I'm scared to write over there, but we can see 70% and 508. Good. Right, so let's do this together. Now, you will be given percentage points for the normal distribution in your formula book. You've also got calculators that have this. You'll have this in your textbooks if you're practicing, but it's in the formula book. Let's look at what we've got. So mu is 425. X is 508. That's our specific one we're dealing with. And we want the probability of x being smaller than that is 70%. So this is really good because you now have calculators that can do the inverse normal function, but I think still a sketch of this goes a long way. So what we know is if we think, why would I expect it to be 70%? Why would I expect it to be more than 50%? Well, if the mean is at 428 and I want the chance of it being less than 508, that value itself is bigger than the mean. So I expect it to be over half the stuff. So that makes sense that it's 70%. So one way we could do this is we could use the standard normal. So we could look up what the 70% value is on the Z tables, on the standard normal. And if the mean is 0, and I want the value that gives me 70% less than it, the Z value is 0.5244. So on the standard normal, that 508 position relates to 0.5244. That's what that means. If I compared this, almost like similar shapes, that's at 0, that's 0.5244. That's basically the same position as R1 is in the context we have. So there's a link there between those values. So 0.5244 relates to R508. So this is where we're going to unpick that graph transformation. So that 0.5244 must be equal to the x value minus the mean over the standard deviation. Okay, so 508 minus the mean over that value must equal sigma. And then we can work back and find sigma. And that means we get a standard deviation of 158.276 meters. So on average, everything's about 159 meters from the mean. So this was using the standard normal to look up key positions, set up the transformation equation, and rearrange. Good. Now, the next part of the question, if we want to calculate the variance, we literally just square that value, square it, and give it to 3SF. So the standard deviation squared is the variance. So that's that bit done. And then finally, calculate the probability. Well, now we have mu and sigma. The chance that it's less than 300 meters is that. So this is just plugging it in the conventional way to your normal distribution. Brilliant. So we're going to just look at binomial approximations to normal distributions, and then we'll do a bit of hypothesis testing, and then we should be wrapping up there. So as I said, I will put up the link at the end for the survey, but let's keep going. You guys have done really well. Let's persevere through this last little bit. So binomial approximations. Now, if in your exam, they say using a suitable approximation for the binomial, this is the only one that gets tested. So this is what they're talking about. So the suitable approximation is just to approximate a binomial with a normal. And this is only done when n is large and p is close to a half. The binomial actually starts behaving like a normal distribution curve. So the way we approximate it, this key little information in the table here, is basically if it's appropriate to approximate, and we have a binomial where x follows the binomial with n and p, we know that the normal distribution is mu and sigma squared. Mu is equal to n times p, and sigma would be equal to root n times p times 1 minus p. So this is the key thing to note for approximating. So like I said, if they say using a suitable approximation, it will only be this. There's a few key things to consider. So let's have a little look. Now, because we're going from a binomial, which is discrete, to a normal, which is continuous, you have to do this thing called a continuity correction. So for example, so what you do is you basically have to give it some width to catch the value. So if in blue on the left, I said I want the probability that x is less than or equal to 7, when we've approximated it, what I'd actually have to do with the binomial, with the normal, is the chance that x is less than or equal to 7.5, so that I fully catch the 7 value. Now, if on the binomial, I wanted probability that x is strictly greater than 5, that would be chance that x is greater than or equal to 5.5, because I want to catch 6, I don't want to catch 5. So these are like really important. And finally, if I said on here, I wanted the probability that x is equal to 9, that's the probability that x is between 8.5 and 9.5. So we'll look at a little example, and then we're going to move into hypothesis testing. So as I said, this is the main approximation they could ask you to do. They're the only two distributions you've learned. So seahorses can give birth to up to 2,000 babies at once, with each baby having a 0.48 chance of being male. So considering a seahorse that gives birth to 1,500 babies, calculate the approximate probability of there being more males than females. Right, quite a nice little question. I think a minute and a half, then I'll whiz through it. And then we're on our final conclusive bit, which is hypothesis testing, which will bring it all together. So give this a go, and then we're going to check it and do hypothesis testing. See how we go. Cool. So we're going to go through this, and then we're going to look at the hypothesis testing, which will involve a bit of normal, bit of binomial, and a bit of PMCC as well. So let's have a little look. So for this one, nice question, 3 marks, suitable approximation. Well, there's only one we've done. So let's have a little look. So 1,500 babies are being born. So N is 1,500. Probability of it successfully being a male baby that we're like looking for is 0.48, so 48% of the time. And we need more than 50% of the 1,500. This is confusing. So we need to just be careful we work out the actual amount. So we want more than 750. And it doesn't say 50% or more. It says more than 50%. So that's a strict one. Okay, so n is large, p is roughly 0.5, so it's appropriate if they ask you. So we're going to do n times p, which will give us the mu value, and n times p times 1 minus p square rooted, which will give us the sigma for our normal distribution. So they're the values we have. Cool. So we've got mu as 720, sigma as 19.35. We're going to apply a continuity correction. So since we want strictly greater than 750, we're going to use 750.5 so that we catch 751 onwards. So then we're just going to do that straight away on our calculator. And the chance of greater than or equal to 750.5 is 0.0575. So about 5 and a bit % of the time, this will happen. So this is, just bear in mind that with these questions in the real exam, because they're going to be big questions, they might actually ask you to do it as a binomial first, then use a suitable approximation and do it as a normal as well, and compare how close they are. But you just had to tweak a few things in order to turn it into a normal distribution. Right, I think let's keep pushing ahead. So hypothesis testing, bit of language to go through. This is the final little bit. So some keywords. We perform a hypothesis test to determine if a sample provides significant evidence that a particular population parameter has changed from what we previously believe. So the hypothesis is the statement made about that parameter. The key notation here is the null hypothesis and the alternative hypothesis, which we call H1. So e.g., the probability of heads is 1/2. That's what we believe to be true if it's a fair dice. That's the default position. Now H0, the default position, make sure you put a colon and then put P equals 1/2. Don't ever say H0 equals 1/2. You won't get any marks. H1 might be probability is less than 1/2, if that's what we're contesting. Okay, so we're going to look more at the language of this now. So the significance level, this is generally, well, it will always be given to you, but this is generally like 1%, 5%, or 10%. But they'll give you this. They'll always tell you what you're using. And this is basically like the scope of how much we're going to give it. So the significance level of a hypothesis test is basically the threshold for the observed value for which H0 is rejected. So it's basically, is it extreme enough for us to say, yeah, the model's wrong? Then a test statistic is basically like what actually happened. So e.g., 1 head out of 10 flips. And then the p-value, the probability of the observed sample of a test statistic, is assumed to be correct. So basically, this is what actually the probability we get. So if we were to work out the probability of 1 heads, given that p is 0. So this is like the probability we're actually calculating to perform the test. So some other keywords, critical region for a hypothesis test is basically the set of values that would cause us to reject a null hypothesis. So if it lands in the critical region, we throw out what we used to believe, and we now take H1 as what we believe. And the critical value is the value of the boundary that makes us first do that. So, for example, here, the critical region might be this stuff if it was below 5%, and this one would be the critical value. So if I got 1 heads or 0 heads, then that would cause me to change my mind, but 0 or 1 would be the critical region. So the critical region are all the values that would make me change my mind. The critical value is the boundary one, the most extreme case that I'd first change my mind. So looking a bit more at the language of hypothesis tests, we also have one-tailed and two-tailed tests. So one-tailed is when the words in the question tell you it in a specific direction, like it's more, it's got better, it's got worse. Look out for those key bits of language. It's improved, it's got less likely. Two-tailed is just, it's not what it was. I think it's changed. I think it's not the same. So that would be two-tailed, and that's basically when it's not equal. So here we go. The actual significance level, another sort of key bit of terminology, is basically you use the probability of the critical value. Okay, so for this one here, this is the actual significance level. It's the probability of the one you actually choose as the critical value. So if the significance level was 5%, less than 5%, and this one, 1.07%, was the closest we could get to that, being below it. That's the critical value. But the actual significance level then becomes the probability of that thing, that tail, because it's not really 5%. It's going to be less than 5% because that's the actual thing you could get. So it's going to be less than 5%. So let's look at a question. So we'll carry on with this one together. So for each of the following hypotheses, state whether it will be one-tailed or two-tailed. So Martin's average score during a weekly game of bowling has increased. A die is biased towards sixes. There is no correlation between the number of awards won by an actor in a film and the box office revenue of the film. So we're just determining what we think. We're going to do these 1 mark for each one very quickly. Let's look at it. So basically, for the first one, it's a one-tailed test because it was a directed thing. The wage has increased. So we almost didn't need to go through all of that. The word increased told us it was one-tailed. The second one is that it specifically got greater, so it's one-tailed. So then the final one is that the correlation has changed. There's no correlation. So this is two-tailed. So because it's a not equal sign, it's a two-tailed test. Right, let's keep going. Now, hypothesis testing for the binomial distribution. We are almost there, guys, so we're going to keep going here. Let's have a little look. So for H0, we're going to say the probability is what we think. For H1, we're going to say the probability, say, is less than P0 if we think it's got less or it's changed. Okay. And then we're going to look at if it falls into that situation. So the direction of the critical region tells us what way to check the test statistic. Right, let's have a little look then. So here's an example. So test at the 1% significance level if the probability of flipping a head for a coin is less than 1/2, given that the coin flip results in one time in 10 flips. So I'm going to do this for you here. Let's work this through. So H0, null hypothesis, is we believe the default position is the probability is 1/2. The alternative hypothesis is that it's less. This here is the test statistic. So we want to work out the chance of less than or equal to 1. So you could use the binomial cumulative, or if you used to use the PD function, you could do x is 0 and x is 1 added up. So n is 10. We want 1 success and 9 fails. So the p-value we get equals. So if you do that on your binomial cumulative, less than or equal to 1, you should get 0.0107. So bearing in mind, this was a binomial distribution with n as 10 and p as a half and x as 1, less than or equal to 1. Now, we've got to think about what this tells us. So because this is this answer here, we do not reject H0 because it's not smaller than 0.01. It's bigger. So it's not extreme enough. Okay. If the chance of that happening was more rare than 1%, it would cause us to throw out what we originally believed. It's above the cusp of the threshold of what is extreme. So we can't reject H0. And I would also put this back in context. So I would say I have to consider that I still believe that the coin probability of success or getting a heads on the coin is 1/2. Cannot reject H0, therefore keep the probability the same. Right, so let's have another little look then. What I might do here is this question is just further practice of what we've done. This may be one, I'll just check if we'll get the solutions for this through. Cool. So guys, what I think we'll do for time, this question here, another brilliant one and consolidation of what we've done, is you could attempt this yourself and you'll get sent the answers for this after, because I'm mindful of the time. Provided we'll answer the survey at the end, you'll be sent all these solutions. So I'll skip through this one and just finish the final part, which is the other types of hypothesis testing, and all the final questions that are left to fill in are for you to do, and we'll send you the answers. Let's just get these final bits of notes down. Just for us, so we're happy with these final ideas. So for a normal distribution hypothesis test, very, very similar. H0, the population parameter we care about, is mu, and that's what the alternate hypothesis is going to be measured against. Okay, so make a note of that. And what you're also going to be doing for normal distribution is it's for a sample mean. Notice this X bar is for sample means. So this is slightly different, and this is probably worth making a note of if you haven't got that. So what this does is this gives the probability for a sample having the same mean, so that it reflects the true population. So this is the way that hypothesis testing will come up for normal distribution. It'll be to do with the sample means. Okay, so I'll just kind of explain that again. But we're looking at like a tail of events. So a sample that's carried out for the whole population, the notation for this, I mentioned it earlier, is X with a bar above it. The population mean is mu, which we use for the normal distribution. So if we take like a sample of 10 things, the mean should be the same, but the standard deviation is transformed in a way that it's sigma squared over n as the variance. So sigma squared over n rooted. So that's what we're talking about there. So we've got this new normal distribution to create and to look at. And then we can kind of compare that to the information we have. So we'll quickly look through an example of this, and then we'll finish with the PMCC. So here we go. Cassie thinks her dad needs to fix or replace the internet router, but her dad disagrees. Their internet speed varies following a normal distribution with standard deviation 11 and 3 speed tests are taking place. So that's the sample. And the mean is 37.3. Last month, their mean download speed was 46.2. And we want to use a 5% significance level to test this. So let's have a little look. So again, you will be sent all of this, but if we list the given information, H0 is that mu is what we believe. And or Cassie thinks that it's less. So that's what we're testing. And the test statistic is that we actually got 37.3 when we trialed it. And that was out of 3 tests. So the number in the sample is 3. That's what we divide by. So for the sample mean, we take the sigma squared over n. We have to be really careful inputting this into the calculator. We keep the mean the same. So we still keep the mean we believe as 46.2, but we do 11 squared divided by 3. And obviously, when you put that in your calculator, you root it, because I think the calculator asks you for sigma, not sigma squared. So you'd have 11 over root 3. And so if you do that, and you look at the chance of less than or equal to 37.3, that comes out about 8% of the time. So that is not significant. That is not below 5%. It's not extreme enough. So when we put in sigma as 11 over root 3, mu as 46.2, our test statistic is 37.3, and we look at the probability of that happening, that will happen about 8% of the time. So it's not rare enough for us to throw out our initial view.